Thank you very much for the invitation. It's always really nice to be here. So I'm talking about Kontsevich-Zagier periods, or rather an analog of these invalued fields, and this is joint work with Mathias Stout. But first I want to discuss this Kontsevich-Zagier conjecture just in the real numbers. And afterwards I'll talk about it in QP and then move on to a motivic setting. Okay, good. So first, let me define what a period is. So a real number. So they're basically special values of integrals. So it's a real number of the form an integral of a function f of x over some domain P, where both f and p are just semialgebraic sets. So f is a semialgebraic function and p is a semialgebraic set. So I will just write L ring definable, and of course you should take this without parameters, otherwise every real number would be a period. And P, this is a subset of R, is this, well, it's the ring of periods. So it's easy to see that this is a ring. If you add two objects of this shape, it's again of this shape, and also the product by Fubini is also of this shape. And also it's a countable set, just because there's only countably many formulas of this shape. So this was formally introduced by Kontsevich and Zagier in 2001, and this is really a rather mysterious object. So it appears in many different topics, such as differential equations, algebraic geometry, or arithmetic, but we don't understand it so well. So let me give you some remarks. So instead of integrating a function, you can also think of this as the measure under the graph of this function. So then this just reduces to the measure of some definable set. So you can always just assume that f is plus or minus 1 in this definition. That will lead to the same ring of periods. So what are some examples of periods? Well, all real algebraic numbers are periods, just because these are zero definable elements in R. So the interval from 0 to alpha is a definable set for any alpha in there. What else? Well, pi is a period because it's the measure of a circle. So this is a definable set. Other things in here are, for example, log 2, just by integrating function 1 over x. And more generally, log of any real algebraic number is a period. And then there's lots of other stuff. For example, zeta of 3. So there's like integral representations for the Riemann zeta function. So this shows that this is a period, and a bunch of other stuff. So showing that something is a period, you just have to find some good integral which evaluates to this number. Showing that something is not a period is extremely difficult. And when this ring was introduced by Kontsevich-Zagier, there was not even a single explicit number which was known to be not a period. So of course, most numbers are not periods, just because of countability reasons. And in 2008, Yoshinaga constructed a computable number which is not a period. So this was the first example. So maybe some open questions about these periods is whether E is a period. This is not known. And just the fact that we've never found an integral which evaluates to E should be some evidence, I think. Another thing we don't know, so it's a ring, but we don't know whether it's a field. So for example, is 1 over pi a period? This is also open. Okay. So there's this conjecture of Kontsevich-Zagier about periods, namely about equality of periods. That basically there's a small set of very simple rules for integrals which explain any equality in this ring of periods. So this is the Kontsevich-Zagier conjecture. So let's say we have we have the same period, but two different representations of it as some function h1 over z1 and same for h2. Then what this conjecture is saying is that this integral can be transformed into this integral using some simple rules. And for now, the term transformed into will be imprecise, so I will make it precise later. So what are some standard rules for integration? Well, there's additivity, of course. If you integrate the sum of two functions, it's the same as first integrating the functions and then taking the sum. And similarly, there's additivity in the domain. So if you integrate over a disjoint union of two sets, you can just integrate separately and then add them. Secondly, you should ignore measure zero sets. So in this case, our domain is a definable set, so measure zero should mean that it has dimension less than n. So if x is in Rn, dimension strictly less than n, then integrating over x should always give 0. Then there is change of variables. So if f from y to x is a, or did I do x to y? X to y is a definable bijection, which is C1. And x and y are open subsets in R to the n. Then if you have some integral over y, you can pull it back to an integral over x. And there's some extra term that appears, which is the Jacobian of x, of course. Okay, and then there's one more rule, which is the fundamental theorem of calculus. So just if you integrate some derivative from a to b, it's the same as f of b minus f of a. And in higher dimensions, you should use the correct analog, which is the Stokes formula. Okay, so this is a Kontsevich-Zagier conjecture, that these simple rules give you explain any equality in this ring. And this is extremely difficult, so we have no clue how to prove anything like this. And maybe just as a very simple example, so zeta of 2 is a period. So again, there are certain representations of the zeta function as some integral. This is equal to pi squared over 6. Well, this is also a period. So what this conjecture is saying, there should be a proof of this fact, which is completely elementary, which just uses, change of variables, fundamental theorem of calculus, some stuff like this. And such a proof was found by Calabi in the end. But that's before this conjecture was a thing. Okay, any questions so far? Yes?
Is it not an open problem whether there is any element that is a period whose inverse is not a period? Or is it known that the periods do not form rigid?
No, this is open. Yeah, this is open. Yeah. Yeah, this 1 over pi is just a concrete example, but we don't know if it's a field or anything. Okay. Next I want to discuss analogues of this in valued fields. And first I want to look at the p-adic case. So, okay, if we want to do an analog of Kontsevich-Zagier, we need two things. Namely, we need this notion of a definable set, and we need a measure. So for a definable set, or for a notion of definable sets, I will just work in the language of valued fields, which is maybe just addition and multiplication in the symbol for the valuation ring. I only care about what sets are definable, not how they are definable. So you can pick your favorite language of valued fields. And for the measure on QP, I will use the higher measure, which I denote by mu p. So this is a general measure which exists on any locally compact group. But the only things you need to know is that mu p, this measure of zp is equal to 1, and it's invariant under translation. So if I take any measurable set u and I translate it by an element x, I preserve the measure. And this determines the measure uniquely. So maybe as an example, if you want to compute the measure of pzp, well, I can cover zp with p translates of the ball pzp. So the measure of this should be 1 over p. And more generally, if you look at the measure of an open ball p to the a times zp, it's always 1 over p to the a for any integer a. Okay, so what's the ring of periods in this case? It should again be like measures of definable sets. Now, in this case, the ring of periods will be much easier. So if X is a definable subset, I will always mean definable in this language without parameters. So if it's definable, then its p-adic measure is always a rational number or infinite. And also the converse is true. So if I take some positive rational number, then there will always exist a definable subset of QP, I think even, whose measure is equal to Q. So this is saying that the ring of periods in the p-adic case is really just the rational numbers. So this is much simpler than in the real case. And in particular, like all links with transcendental number theory are lost in this case. But this should already be a good indication that this Kontsevich-Zagier conjecture is much easier in this setting. Okay. So now let's try to make this conjecture more formal in this setting. So I'll define some formal ring which keeps track of these relations in the Kontsevich-Zagier conjecture. Definition. So R is the ring. And also In this case, I will only be, instead of considering integrals of definable functions or something, I will only work with just measures of definable sets. So it's as if you try to do this thing, but all the functions are equal to 1 in this case. So what is R? R is the ring generated by elements of the form the class of X, where X in QP to the n is definable and maybe bound, let's say bounded. With following relations. So we're going to try to mimic these 4 relations in the Kontsevich-Zagier conjecture. So first one is easy. This is this additivity. So namely the class of X is the class of X minus Y plus the class of Y if Y is a definable subset of X. For measure 0 sets, so definable sets in QP in this language, they have a nice geometry. So, for example, I mean, all definable sets will have a dimension, which is an integer between 0 and n, the ambient dimension. So if X in QP to the n has dimension strictly less than n, then the class of X should be 0. Then next is change of variables. So suppose we have 2 open subsets in QP to the n and some definable bijection F between them. Now QP is a topological field, so things like derivatives make sense in QP. And so we, similar to over there, we want to require that F is at least C1. And for simplicity, I will assume, I mean, we also need to use something with this Jacobian. So we will just assume that this Jacobian is a unit, so the valuation of the Jacobian is always 0. Then what is this map F? Actually, this will be a measure preserving definable bijection between X and Y. So the classes of X and Y should be the same in this ring. Okay, and finally, what's the fundamental theorem of calculus? Or more generally, what's Stokes? This is just a relation that X times the ZP is equal to X. Okay, so this might look a bit strange, but I feel like this is because definable functions from QP to R, or like their norms, they are locally constant, so it's a lot more rigid than this situation over there. Okay, and okay, it was maybe not explicit, but the product in this ring is just a Cartesian product of definable sets. Okay, so if I have 2 definable sets, then equality in this ring R is exactly saying that X can be transformed into Y using these kind of standard rules for integration. I have more room over here. So, in particular, if you look at the map, the p-adic measure, it's now a morphism from this ring R to Q. So why is this? This is simply because the p-adic measure satisfies all of these rules, like additivity, change of variables, and so on. And well, we already know that it's surjective, because for every rational number we could find there is some definable set with this measure. And so the analog of Kontsevich-Zagier would say that this is an isomorphism, and that's a theorem due to Cluckers-Halupczok. Okay, now I'm phrasing this in using this Kontsevich-Zagier conjecture, but another way you could interpret this result is that this ring R we defined, it's kind of the universal object for integration for definable sets in QP, in the sense that if you have any integration theory for definable sets in QP, it has to factor through this ring R. And so what this result is saying is that the universal theory of integration of QP is just p-adic integration. This? Yeah. Yes, yeah. I mean, the reason it's true for mu p is because ZP has measure 1. Yeah, yeah. Yeah, and also in these relations, this is the only relation between sets in different ambient dimension. Like the three above, it's only about sets x and y which live in the same QP to the n.
Sorry, philosophically, what's a definable function to
Yeah, maybe the norm of a definable function on QP, something like this. Okay, so let's see. So what we do is we study an analog of these questions, but in a motivic setting. So for the rest of this talk, I will work in Lorentz series over C. So this is a valued field with valuation ring the formal power series. Yeah. I mean, our results work much more generally for other henselian valued fields. If you're working in some 1H minimal theory with some extra assumptions, then everything I say will go through, but the results will just be easier to state for this context. Okay, so for Kontsevich-Zagier, we need again these two ingredients, definable sets and measures. So for definable sets, I will work again just in the language of valued fields, together with a constant symbol for t, which you really need to make things work. So that's easy. So whenever I say definable, I mean in this language. But the measure is, I mean, a lot more tricky to define because this is not a locally compact field, so there's no high measure or anything. And so we replace this by some kind of motivic measure, which takes values in a different ring, which I want to define next. So it already appeared in the previous talk, but let me recall it. So first we need the Grothendieck ring of varieties over C. So this is the ring generated by classes of the form X, where X in C to the n is, let's say, just L ring definable. Or alternatively, you can use algebraic varieties defined over Q. And there's two relations. So first, there's again this additivity relation. If I have some definable subset Y of X, then the class of X is the class of X minus Y plus the class of Y. And secondly, if F is some definable bijection, so L ring definable bijection from X to Y, then the class of X should be equal to the class of Y. And I will denote by L the class of the affine line in this object. So this is not quite the ring of measures where this motivic measure will take its value, so it's slightly bigger. I'm going to denote it by C. So this is this Grothendieck ring of varieties. You need to invert L, and then there's other elements you need, which are of this form. So it's 1 minus L inverse divided by 1 minus L to the minus I. So if you work a bit, this is the same ring as if you were inverting projective spaces. That will be the same. So this will be the analog of the ring of periods. And maybe a small comment for experts on motivic integration. So usually, if you see this kind of ring, there would not be a numerator. And like in Cluckers-Zagier integration, for example, you see this ring. So this is maybe a slightly bigger ring. So there is an obvious map from this ring to the one where you do this. But it's not clear whether it's injective in general. And the reason we work with this ring instead is because our language doesn't have angular components. So if you have a language with angular components, you should really use a slightly bigger ring. But then there's a bunch of other problems. So, okay. So what is motivic measure? So, well, I will do it in the style of Cluckers-Zagier. So they assign to every, let's say, bounded definable set X in this valued field a measure mu of X, which lives inside this ring C, and it has a bunch of the usual properties. So it's a finitely additive measure. There's a change of variables formula. There's Fubini type theorems. And actually they do a whole lot more. So they also give a notion of a motivic function, which you can integrate. And they show that these motivic functions are closed under integration and so on. So let me just give you some examples. So if I take some algebraic variety X or just some definable set in the residue field, then I can look at the pullback to the valued field under the residue map. So this is a subset of the units in the valuation ring to the n. So what's the motivic measure of this thing? This will be the class of this set X in the Grothendieck ring of varieties. And there's some small normalization where you have to divide by L to the n. So that's the motivic measure when you pull back from the residue field. If you pull back from the value group, so let's say we have a definable subset of z to the n, then the motivic measure of V inverse of A, so this will become a rational function in L. So and even more, you can, if you plug in for L some prime number P, you will get the p-adic measure of the corresponding set in QP. So this is some kind of specialization from motivic measure to p-adic measure. Does this make sense? Yes, okay. Okay, and in general, how this measure is constructed is using cell decomposition. So if you have any definable set in k to the n, you can cut it up into pieces called cells. And the measure of a cell is somewhat easy to define. And then you just add up over all the cells.
Then the dimension is smaller than the dimension of the empty space.
Yes.
So the measure is no longer zero, like what you wanted over there?
Yes, because if you pull back this residue inverse of X, this will have full dimension. Like if you take a point, just a point in the residue field, for instance, you pull it back, you get an open ball. Yeah. No, I don't think so. Yeah. Yeah, I mean, what goes into this proof, for instance, is cell decomposition, quantifier elimination, all this stuff, and yeah, over FP double brackets T. I'm not sure if we even know that the measure is always a rational number. I'm not sure. Okay, so if we want to formulate this analog of Kontsevich-Zagier using motivic measure, we again need this kind of formal ring R, which keeps track of all these relations. So let's just copy the definition. So I will again denote this ring by R. So this will be for definable sets in k to the n now, which are bounded with the following relations. So Again, there's the additivity relation, which is just exactly the same. If X is a subset of k to the n, well, again, there's a good tame geometry in this setting via cell decomposition and quantifier elimination. So in particular, definable sets have a dimension. And this makes sense, saying that if the dimension is less than n, then the class should be 0. Similarly, for change of variables, well, K is a topological field, so things like differentiability make sense in the same way. And we require, again, that the valuation of the Jacobian is constant and equal to 0. Then the classes, well, then this map F will be like a measure preserving definable bijection, so the classes should be the same. And finally, we are just saying that the class of the valuation ring is a 1. Okay, so then we prove exactly the analog. Right, so maybe first, now mu becomes a ring morphism from this formal ring R to this, I mean, it's more concrete ring of motivic measures. And again, the reason is just because motivic measures satisfies this change of variables formula and Fubini type stuff, that it satisfies all of these rules in this ring R. And so what we prove is that this is in fact an isomorphism. So the surjectivity is quite easy, but the injectivity is, I mean, for surjectivity, you just have to construct definable sets achieving every measure in this ring C, which I guess you can almost already do with these two examples up there. But the injectivity is a lot more difficult. And in fact, okay, so we prove more. There's also a version for semi-rings. So a semi-ring is just like a ring, but you don't have additive inverses of elements. And so there's an analog of the semi-ring R, where you just take the semi-ring generated by these relations, and similarly, there's a semi-ring for this object C. And then this map is still an isomorphism. So this is really a stronger statement, this version for semi-rings. And as I mentioned before, so for this talk, I work in this field C double brackets T, but this result is true more generally for 1H minimal theories, which are effective, plus some extra assumptions about the residue field and the value group.
Is it always the same C?
For other fields, no. Yeah, that's a good point. Then you have to replace, for example, this Grothendieck ring of varieties with the Grothendieck ring of definable sets in the residue field. But even that is not enough. So there will be some rational numbers appearing in C depending on whether you have definable square root functions and annoying things like this. So that's why I wanted to stick to algebraically closed residue field. Okay, so at the end, I want to discuss the proof. Or rather, I want to discuss an example. So I just want to zoom in on one small part of the proof of this result. Namely, I will give two explicit definable sets which have the same motivic measure, and we'll try to deduce that they're the same in this ring R. So this is needed for this injectivity. So to do this, A will be the following set. So I'll take two definable subsets of the value group. So what do these look like? So the set A is just the diagonal in Z squared. And the set B is like 2n times 0. And we'll consider the sets X, which is V inverse of A, and Y, which is V inverse of B. And now it's a little computation, so if you want to compute the motivic measure of X, well, I mentioned before, this one specializes to p-adic measure because X is a pullback of a definable subset of the value group. So if you want to compute this motivic measure, what you can do is just compute the p-adic measure. This will be a rational function in P, and then just replace P by L. And this will give you the motivic measure. So, okay, I don't want to do this computation. So it turns out the measure is something like this, which is the same as the motivic measure of Y. Okay, so for this theorem, we have to prove that X and Y are equal in this ring R. So one way to do this is to try to use the third relation to find some definable measure-preserving bijection between X and Y. And how would you find such a bijection? Well, you can look at purely the value group and try to find some kind of measure-preserving definable bijection in the value group and then just lift it to the valued field. So concretely, let's look at the following map. I'll call it H. From A to B, which maps xy to 2x and y minus x, so we can also write it some matrix. So this is a definable bijection between A and B. Now we want to lift it, so this gives some map H from X to Y. Maybe I should call these things I and J. So what is the map? It's going to be x squared and y times x inverse on the level of valued fields. Now, why did I pick this matrix? Because if you do the computation for the Jacobian, it turns out that this map is measure preserving. So that's good for relation 3. But obviously, H is not a bijection. Simply because there's x squared here. So this is an issue. Okay, let me also discuss what you would do in the p-adic case. So in the p-adic case, there's kind of fake squaring maps. So in QP, there exists some definable bijection from ZP to all elements in ZP whose valuation is even. So one way you could construct such a map is use that in QP, the angular component map is definable. And so you only have to describe this map when the angular component of an element is constant. And if you do this correctly, G will be C1, this map. And the norm of the derivative will be equal to the norm of x, which is the same as it would be for the squaring map. And let's say P is odd. Okay, now in the p-adic case, if you want to lift this map, you can just replace this squaring map with this fake squaring map. So let's call it H tilde maybe. So this is for the p-adic case. I'm going to map xy to x, g of x, y x inverse. And this will now be a measure preserving definable bijection, so by relation 3, the classes of x and y are the same in the p-adic case. But in this case, for C double brackets T, you cannot do this, and in fact, I'm pretty sure there's no measure preserving definable bijection from x to y. So you cannot get there with just relation 3. So no. Okay, so the solution is we need to use some other relation, which is relation 4. So instead, we try to find a measure preserving definable bijection from x times OK to y times OK. Call it F maybe. So I find this very strange. So this does in fact exist, and I will write it down explicitly. So I find it very strange that there's no way to transform this set x into this set y, but you add one more variable, and suddenly you have a little bit more room, which helps you to actually just find such a definable map. And to end, I think I will just write down the map. So also, if you try to do things naively, you will get stuck in the same way. So you will have to cut up this domain into several parts and do different things on each of them. So the map looks like this. We map xyz to x, yx inverse, xz, if the valuation of x is even. We map it to xz, yx inverse, x, if the valuation of x is odd, and the valuation of z is odd, because it needs to land in y, so the first coordinate should have even valuation. And finally, we map it to xzt times yx inverse times xt inverse, if valuation of x is odd and valuation of z is even. Okay, and it turns out that this map is a definable measure preserving bijection between these two sets. And yeah, I guess it's a bit early maybe, but I'll stop here. Thank you.